Okay, so good afternoon or good evening, everybody. Here. So good evening, everybody who came. Good evening, everybody who's online. So we can try and make a start. Okay, guys, so we'll make a start. So it's 5 o'clock, so we'll try and get going. We have a few people waiting online as well. So welcome, everybody. I think this is the first one of these we've done actually together, not online. So although we have a few people online as well, so it's both online and in person. So what to say? So as you know, these are some seminars we've been organizing over the duration of lockdown or over the duration of the pandemic in general to kind of keep in touch and keep up to date on what people are working on, what's going on at IUSS and other related places. And we try and do these about once a month, once every 2 months, just to keep in touch and disseminate a bit of what we're doing online and so on. So it's been a while, I think, during the summer when we had our last meeting. So to make a comeback, we have a special guest tonight, or this evening. It's Professor Calvi. He's going to give a presentation on which was part of a talk he gave at the 17th World Conference. So the talk is on towards a practical loss-based design approach and procedure. So just before I give the floor to Michele, I would just ask everybody who's on the line, who I think they're all connected with that camera sitting over there, to keep your microphones off. The conference or the seminar should last about an hour, so we should have time for the presentation, maybe some questions after. And I think that is it. And yeah, everything is being recorded, so if anybody misses anything, wants to share it, it will be available online on YouTube and the general mailing list and so on. So, Michele, the floor is yours.
Thank you for this introduction, Gerd, and thank you to take the role of organizing these seminars that I think are very important. This is actually not a seminar. I will only try to, put on the table a number of ideas. My hope is that there will be discussion, there will be additional work, and so on. Gera was correct in saying that I presented something like on this subject at the World Conference, so the one which was essentially at a distance. This was an invited presentation at a kind of a strange section, which was the IAEE, which is the International Association of Earthquake Engineering brainstorming session for future directions of earthquake engineering. So this was somehow part of the very short conclusions of the conference that were presented at the closing ceremony that actually took only 57 minutes altogether. So I was admiring the Japanese in their capacity of keeping the final closing ceremony in less than 1 hour. It is true anyway that the subject of, from my point of view, loss-based design, from the point of view of many people, minimum loss seismic design is becoming more and more relevant and important in the general panorama of earthquake resistant design. And this is very different from what has been done in the evolution, I would say, in the last about 50 years. Somehow earlier than 50 years, people were designing, comparing actions and strength, but at a very low level of actions and very low level of strength. After the Messina earthquake, 1908, which was essentially the same time as the San Francisco earthquakes 2 years before, the scientists invented a fantastic way of trying to guess what the acceleration the buildings and the structures were feeling at their, say, equivalent center of mass. And the way was simply, since there were no accelerometers capable of recording anything at that time, they were simply looking and separating buildings that collapsed from buildings that did not collapse, and then trying to evaluate the strength of those that collapsed and those that did not collapse, and saying, okay, the acceleration must have been higher than the strength divided by the mass of those that collapse, and lower of the strength divided by the mass of those that did not collapse. And as you may know, they arrived to something which was probably in the order of 30 to 35% G average capacity of buildings, of ordinary building of the time. And in fact, they were suggesting to design for 10, 12% of G, because they were assuming that you could have damage and therefore you could reduce the acceleration for which you are designing. So designing at 1/3 of something that was guessed, and already the guess was probably on the low side, means to design for very low forces and for very low capacities. Then, when after the earthquake in San Fernando in 1971, people started discussing about ductility, discussing about acceleration are larger. There have been at that time recording of El Centro in 1940, and in El Centro they actually recorded 0.35 G, but in the 70s they already recorded more than 1 G, for example, at Pacoima Dam. So people are saying maybe the acceleration could be higher than 1 G. How can we design for this? And of course, on the other side, strength is not, say, correlated to something that you should use for 10% G, but to something else. Anyway, if I go ahead like this, I will spend all my time in a kind of an introduction. So I'll try to go a little bit faster. To talk about loss-based design is something that started, I would say, almost 30 years ago, in the sense that the whole subject of performance-based design somehow is related to loss-based. To design for a performance means not to design for strength only, for other purposes. But as you may know, as you may have discussed and studied in your courses and so on, this is very clear from a conceptual, theoretical point of view. But at the end, today, you may apply the old familiar force-based design or maybe better displacement-based design. But what does it mean, loss-based design? So let's try to go into this subject. The objective is clear: minimize the total investment, where total investment is what you spend to construct, what you spend to strengthen, what you spend to repair, and so on and so forth. And this will become more clear in my next slides. And of course, this is difficult as an objective to be obtained, because the correlation between loss and strength is rather weak, and the correlation between loss and displacement is better, but still probably not essential. There are, of course, approaches that have been developed more for assessment than for design. For example, probably all of you here in this room are familiar with the approach of the FEMA P58, and you are all familiar with the separation between hazard characterization. So first step, depending on where you are, you define hazard. And hazard is not only a certain acceleration value or a certain displacement value, but it is an association of intensity in terms of acceleration, displacement, and so forth, to a return period or a probability of exceedance over 1 year or over 10 years or whatever. Second step is familiar to all of you, is kind of a conditional integral. So you look at the response of the structure, and now you have on one side the intensity expressed as acceleration, displacement, or whatever, and the other side you already have consequences in terms of structural parameters. So for that input, you are going to have that displacement or that in-the-story drift or that floor acceleration or whatever. And then the third step is, as a function of the level of each one of these response parameters, you try to figure out what is the consequence in terms of loss. And in many studies, loss means direct loss, but as I will discuss, indirect losses are often much larger than direct losses, and therefore they are more relevant. And then the last step is a kind of a decision making, which is exactly what we mean when we say loss-based design. So what you see there, MAFE is the mean annual frequency of exceedance. As a function of that, you have a certain value. So you are conditioning, and then you can go from hazard to what you are expecting in terms of loss. Of course, when you talk about the second step, which is the one that we have been spending more time on, you may remember something like this. This is something I presented in Lisbon, I believe, at the World Conference in Lisbon, and then it then became a paper saying, look, you could use some kind of pushover representation of the response of your structure for a building in this case, and then you could say that for that level of interstory drift, the one that you can see here. Can you see my? No, you cannot. Okay. The level of the interstory drift that you can see on the right corresponds to that point that you can see on the left. And therefore, you could say that at that level of performance, you may expect a certain level of interstory drift, which means a certain level of expected damage, a certain cost of repairs, so on and so forth. And for this other level, you have another interstory drift and another kind of consequences or series of consequences and so on and so forth. So you can somehow associate some parameter that correlates response of the building and expected level of damage. We will talk about damage and loss soon now. Now, when we talk about loss-based, it has become rather clear in the last years that the main parameters that we're going to use is called expected annual loss. What is expected annual loss? Expected annual loss is an integral of probability of occurrence times level of damage. If you consider that integral, so you take a figure like this, which is only qualitative, you have on one axis the probability of occurrence, on the other axis, say, for example, the expected direct damage. What does it mean? It means that if you are up there at in the top part of this drawing, you have a probability of occurrence which is high, which means that the return period is short. And it could be that at the point at the tip there, you have maybe 10 years or 20 years or 25 years or whatever. What does it mean? It means that it's the threshold level. For a higher probability of occurrence, you are assuming that the damage is below whatever you want to consider. Otherwise, you cannot. You will go to infinite, and you cannot. We do not like to deal with infinite numbers. If you look at the other side, at the point that you have to the right, there the probability of occurrence is low, and if the damage is 100% in terms of direct damage, it means that it is collapse or a state of damage which is so high that it will be more convenient to demolish and reconstruct the building. So that point could be 100% in terms of damage and could be maybe 1,000 years or 1/1000 or something like that, or 1/500 or 1/2000 and so on. So you have the two opposite points. Okay, 10 years threshold level, 1%, 2% cost of repair. And then you are conditioning the entire curve with something in between. We cannot afford to take many points in this curve. But can we accept to have two straight lines defining only one point in between? The answer is probably we cannot, because the actual curve, if you try to depict the curve, is normally very steep on both sides. So the difference, if you look here, the difference between the integral, so the area under the blue line and the area under the red line, they are very different, 2 times, 2.5 times. So we cannot do that. We need to have some sort of representation of the entire curve that is not too far away from what actually happens. And I don't have time to discuss this, but this is an equation that I developed. I like it very much. You will understand why I like it very much. But anyway, let me say that this equation appears to be complex, but it's quite simple because there is only one parameter. The parameter is that alpha that you see as an exponent to the sinus and you see 1 over alpha as the exponent of the content of the reverse of the cosinus. You may wonder, how do you come out with something like this? I mean, this is very strange. You imagine some of you maybe knows, but some other can imagine how did I come up with an equation like this? Okay, it's simple, because I was looking for an equation that with only one parameter was able to modify completely the shape of the curve, but keeping 2 points fixed. And therefore only modifying the fact that it could be a straight line, could be thinner and thinner, but actually the same equation could also go to the other side. And that equation where you have the sinus of 1 over 1 cosinus is the equation that we use to represent the response of a damper. And in a damper, you know that if you have say 0.1 at the exponent, it tends to become close to a square. And if you increase that, it goes down and down and down. It works beautifully. So you can just modify that parameter. You can have all sorts of curves, which means that if you looking at this from another point of view, if you fix the intermediate point, whatever you want to fix, I mean, you could say, I want 20% damage with a probability of occurrence of 1 over 50 years, or 30% damage with a probability, whatever you pick up, it corresponds to a certain value of alpha, or vice versa. So what I'm trying to tell you is something like this. If you accept to define the 2 points, for example, I don't know even what I've done here. You see, 2% at 20 years is the threshold. You don't care about the damage below 2%. Below 2% is nothing. And you have the other point that is here. I don't know what I use. Maybe. Anyway, the other point is written there. I'm not sure. Anyway, 1,000 years, 100%. Now you see what happens. It happens that you can correlate the expected annual loss, which is here on this plot on the vertical axis, to alpha. So somehow, modifying alpha, you are modifying the shape of the curve. And you come out that maybe a possible equation, but here there are many young students. You can take this and do a lot of analysis and find out that I'm completely wrong and say, no. You should not put 6%, you should put 6.2%. And then to come out that instead of putting plus 0.5%, maybe 0.53%. This is fine, but you understand what I'm trying to do here. I'm saying that if you decide that you want an expected annual loss of, say, 1%, you could know what level of alpha you should use, or vice versa. So the expected annual loss could become a real tool for design. You understand what I mean? A real tool for design means I'm accepting this level of damage. And of course, as a function of this level of damage, I will assure the building for that value, and so on and so forth. There are huge consequences if you accept to do something like that. And if you look at what maybe is happening today, you see in that single line table that maybe you are in the range of 1% expected annual loss, direct loss, cost of repairs, and so on. Maybe if you have an alpha which is around 4, something like that. You know what that means? What this does means? You know, look at here. It's like saying, if you take all these curves are different curves, and they are characterized by a different alpha. Or if you want, they are characterized by different values at different level of different values of alpha of the annual probability of exceedance and different values of the expected loss average per year. And if you take 72 years, as you know, is the probability of occurrence of 50% in 50 years, which is often the figure that we use in new design for a state of limited damage. And you say that maybe the state of limited damage is 20% of the cost of reconstruction. then you see that you are close to the green line, and the green line is expected on a loss 0.8%, maybe slightly higher than that. I'm trying to conclude in this part that we are often designing without knowing it for something which is in the range of 1% average expected annual loss for new buildings. If you ask or maybe there are here people who works on risk assessment and so on, you will find figures that are much lower than this value. I tend to believe that the reason is that insurance, people working in insurance and in reinsurance do not like these numbers. They are too high because it will cost too much to insure a building if this figure should be true. So it's the opposite way. You know, we should insure for the money that the owner can afford to pay. And we start from there, not from this side. But anyway, I'm ready to discuss this. And don't forget that I've not yet talked about the indirect losses. So this is exactly what I was trying to tell you. But there is one more point I want to underline. And let me go back. Then I'll come back here. You know, the other point I want to underline, maybe here, is that if you are designing a hospital, for example, what will be the aim of your design? You want to move the point to the right of this plot because you want to decrease the probability of collapse, or you want to make this curve very steep on the two lines. The answer is the second. You don't care too much if the probability of collapse of an hospital is 1/1000 or 1/2000. What you want to have is the hospital working after an earthquake, correct? So what you really want to have is to have low damage after a major event, which means to have a curve which is similar to the purple one, or at least to the blue one. It's completely different. You don't want to have more strength. You want to have less damage. You want to have the building working. So let's go ahead on this. And what you see in this plot is that the correlation between expected annual loss and one intermediate point of control is very strong. But to modify the other 2 points, the threshold value and the probability of occurrence of collapse, is not changing very much the shape of your curve. The losses are not significantly affected if you modify the probability of occurrence of collapse. So let me now have a quick glimpse, because I'm going much slower than what I should, a quick glimpse into indirect losses. Indirect losses essentially is business interruption. As I already said, that for a hospital, it's not relevant. You want to have the hospital working after an event. But for other building or bridges, it may be relevant. So let's look at the simple case, residential case. Suppose that to relocate a person that remains without his place to live costs to the society, doesn't matter who is paying. I'm not talking for insurances or for the state or whatever. It's, for example, 35 euros or dollars per day. And suppose that the cost of reconstruction is 1,000 euros per square meter. And suppose that in the average, a person occupies 25 square meters. All assumptions. You can change these figures. If you accept that, and then you consider that maybe if a building collapses, so 100% damage, maybe the time for reconstruction is maybe 2 years. Then you do a simple calculation and you find out that the ratio between the losses due to indirect costs that here are defined as relocation of people and the cost of reconstruction is about 1, which means that are in the same order of magnitude, okay? Or that if they are in the same order of magnitude that you take 2 years, maybe the cost is 0.14% of the total cost of reconstruction per day. But if you do the same calculation for bridges, for example, and of course here you change your point of view and you say, I have a certain number of vehicles crossing the bridge. These are very easy data to be taken out. And then you know what is the tour length. If you don't have a bridge, if you cannot pass on a bridge, how many kilometers do you have to go? And then you consider a cost per kilometer. You are consuming gasoline, you are increasing pollution, you are doing this and that and that. This is general societal cost. And then you do the same thing. You find out that for important bridges, that does not mean necessarily long bridges. It could be an overpass on a freeway where you have 10,000 vehicles per day. So a small bridge. Then you find out that the indirect cost could be much higher, could be 5 times. If you go into the industrial problem, it's impossible to do this calculation. You can only go and interview the owner and ask him, what is for you the cost of stopping your activity? But then you should also remind him that his cost is also losing the clients that will go somewhere else. It's very difficult to conquer again a market if you lose it. Anyway, if you assume this, then you could have plots like this. This again is a curve that you know very well. This is simply the same equation as a fragility curve. Why I'm using this? Because I think that if you have small damage, the indirect losses tend to grow slowly because the indirect losses depends on the impracticability of the structure. And then they go up fast. But when you are close to a collapse, you probably will not be able to use your structure even if it does not collapse, so it's flat again. So you use something like this and you do all your exercises and you come out with something like this, where the equation that I showed you earlier, which was expected annual loss equal 6% divided by alpha minus 0.5, or the reverse in the other way to alpha, now seems to be a little bit more complex, but not that much, because here there is RI over D, which is the ratio of indirect to direct losses. And this comes out with something like this, and you know the dots are calculated points, and you see that this is not too bad again. So what happens is that if you include the indirect losses, your losses are increasing very significantly and in a nonlinear way. And in fact, you can obtain curves of this sort. Here now you have again the expected annual loss on the vertical axis, and you have a return period for 20% for a ground motion inducing 20% of direct losses. And you see that the blue line is the line that we were seeing earlier. If you have 5 times as ratio of indirect to direct, you have the black line. So you see that your expected annual loss is increasing very much and is raising up rapidly here. So this kind of curve is telling you that probably your target design, if you look only at losses, is probably something in the area where the curves is not steep anymore and it tend to become flat. There is no reason to design for a point close to the end of this curve, because you are not increasing the quality, you are not increasing your saving. It will not be convenient. You should go to a point where you're still decreasing, and then you go. So it means that for the black line, you will move to the right with respect to the blue line. So it means that you will design for 20% for a longer return period or a lower probability. If you have more damage, if you have more loss, if you are expecting more loss, you want to design for a lower, to have a lower probability of having an input ground motion that will induce the same level of damage. Okay. Now I will go very quickly because I've already discussed in other seminars here, and maybe some of you were here. Of course, there is a number of ingredients that enters this discussion from a practical point of view. One ingredient is the definition of seismic input. There is there Guido Andreotti that has been working with me on this a lot. You may remember, if not, go back and read again all this about what happened between the 40s and the 70s, where the spectra were defined. And you probably are familiar, or you will be familiar with displacement-based design, where the logic is instead of using a force reduction factor, which is maybe 3 or 4 or 5 or 6, so I have a huge change, I will only use a correction that takes into account the dissipation of energy, and this correction factor is probably in the range of 0.6 or 0.7, certainly not larger than 0.5 or 2 if you want to use the reciprocal. And in fact, here you can see that using many different possible equations, you see that just for a reactivity of say 2 or 3, you are in a range which is 0.6 plus minus 10%. If you are in that range and you're talking about preliminary design, conceptual design, that's good enough. I don't want to have anything better than that. Okay. And then if you go ahead, and this, I don't want to spend time on this. This is my view on how to revise spectral shapes, but this is not the subject of today. So if anyone is interested, just talk to Gerard. I give another seminar on the subject. We examined some 7,000 ground motion on different kind of ground motion to try to define what is the expected spectral shape as a function of magnitude, distance from the epicenter, and soil condition. Finding out, I would say, tendencies that were obvious 50 years ago, in the sense that if you have a strong earthquake and the location which is close to the epicenter, which means that you have a large acceleration, it is possible that for a soft soil, the soil will go into the nonlinear range. If that happens, you will increase the displacement demand, but will not increase the acceleration demand. The acceleration demand is governed by the capacity of the soil. On the opposite, if you have the same earthquake, but you go further away from the epicenter and the demand decreases, the soil will not go into the nonlinear range. And therefore, you may have a larger amplification in the acceleration that is now not capped by the response of the soil. So all this allows to define spectral shape like these ones. Our shape are the red ones that, depending on the probability you want to use, probability means to go for a +1 sigma or +2 sigma with respect to the average conditions. You can have a different shape, and remember that in the vast majority of the spectrum, which is what once was the so-called constant velocity, conservation of velocity region. If you use the conservation of velocity, you have something where the curve goes down rapidly, so it's concave. But here you have convex response in certain cases, which means that if you think in terms of a pushover curve that intersects this, the intersection point could move away a lot. Account for energy dissipation. Again, I don't want to spend time on this. I plan to finish in maximum 10 minutes. But in the last years, often I have been wondering why we should take a parameter which is a structure parameter, and use it to correct the demand instead of correcting the capacity. If you have a response which is elastic, like the one to the left, or you have some dissipation, like the one in the center with a yellow area, or you have more dissipation, what happens is that the displacement demand reduces. So the blue curve becomes shorter. You are dissipating energy, therefore you have less. So this means that you are modifying the displacement demand, but you are not much modifying the acceleration demand. And therefore, you are modifying the equivalent period of vibration. If you look in terms of what we have done in the past and we are still doing, if we take an elastic spectrum, then you take this point and you move it down here. In this way, you are conserving the period and modifying the acceleration. You see, you are going along the yellow arrow. not along the green arrow. If you want to go along the green arrow, that point should not go there, should go there. You want to keep the acceleration and reduce the period. So that point, the point should go, the difference is that in stiff structure, you're not a benefit. This is what our ancestors were doing in the 70s. Conserve acceleration for very stiff structure. So you have a different shape, and this can have consequences. Now, design for loss control, so that I keep my promise to finish in the next 5 or 6 minutes. Suppose that now you are able to define a number of spectral shapes like the blue ones, like the blue one here, because there is only one here. And that's the shape that you want to use for a long return period case. So you have a large magnitude at a close distance. Okay, and then you have a number of other cases in which you may have a large magnitude at a longer distance, or you may have a smaller magnitude at a closer distance, and maybe you have spectral shapes like the black or the red one. What does it mean? It means that probably you may say that the blue one here has a probability of occurrence of maybe 1/1000 per year, and the red and black have a probability of occurrence, you tell me, of 1/100 or whatever. Now, if you want to design to contain the loss, the black and the red shapes are fundamental. And you want to limit the acceleration, the floor acceleration, because there are elements that are sensitive to the floor acceleration. And you want to limit the displacement or the interstory drift because there are many more elements that are sensitive to that. So what you may wish to do is to cap horizontally the maximum acceleration that you are designing for, and cap the maximum displacement you are designing for, which means that you have to design a structure that, for this rather frequent event, should stay between the red and the black arrow. If you have a stiffer structure, you might have an excess of acceleration and a certain kind of damage. If you want to have a more flexible structure, you may have other kind of damage because you have a larger drift, interstory drift. So you can have doors that could not open anymore, and so on and so forth. So you're not free. You should stay in there, and you are still in a response which is not necessarily elastic, but close to be elastic. The structure has not yielded yet. And then when you take the blue line, okay, this is just what I was telling, cap the acceleration, cap the displacement, and then you stay in there. And then if you then look at what happens with the blue line, you will find out that you cannot design for the blue arrow, that you may do if you look only at ultimate situation, because you want to have a stiffer structure for frequent events. So you need again ductility, you need again displacement capacity, because you want to stay in low damage. You want to have a relatively stiff structure. But of course, this applies to a building where you can accept to have a situation that maybe has some significant damage for a low probability ground motion. If this does not happen, what happens? Look at this. I mean, if you want to design for continued use in case of a rare ground motion, it means that you want to cap acceleration displacement with reference to the blue line. But if you take the same cap as before, the intersection is near. There is no possibility, because you want to stay to the right of one line and to the left of the other one, but in the wrong combination. So there is no solution. There is no solution, and what happens? It means that you have to find other solution. What could be other solution? You cannot stay as I was saying, you cannot, the intersection is, if you want to stay lower than the blue one and higher than the red one, there is no possibility. But could you accept to do something like this? And here is where you have a few options. One option is to design non-structural elements capable of taking larger acceleration and taking larger displacement. So you may have a hospital that behaves like another structure, but where everything that is inside is not sensitive to what's happening. Or you could have another solution, which is recur to isolation or to tune mass. This has not been rationalized in the past, but I remember many years ago, I designed an isolation system for a nuclear power plant in France. And I was wondering, why should I design this isolation system? It doesn't make any sense to me. There is so much strength here. But then the things became clear to me. The point was that having an isolation under that structure was reducing of many times the acceleration inside that big mass that was essentially infinitely stiff. So the acceleration that whatever was inside the nuclear power plants would have been the same acceleration as the solid. But if I put a base isolation, it becomes maybe 1/10 of that. So there was a good reason that had nothing to do with the strength of the structure, nothing. Okay, so I'll try to conclude. We today are dealing with displacement-based design that is probably today the best tool, but we can work on this procedure to try to improve our capacity. At the end, we will have any way to say what should be the size of a column or the thickness of a wall or whatever. We will go at materials at the end, but with something different in mind. And in a paper that recently appeared in Engineering Structural Dynamics, we have tried to describe a possible sequence of steps to design according to these criteria, and the sequences of steps to assess according to these criteria. This list of 10 or 12 points is a real indication of what to do. It's not philosophy, but there is a long way to go before we have tried this, and we have tried this on different kind of materials, different kind of structures, and so on and so forth. And I stop here. If you want, I show you what was my last slide in Japan, but this is just for fun. My last slide in Japan was looking forward to see you all in Milan in 2024. I hope that this will induce some of you to think and to say I'm totally wrong. I'm old enough to easily accept that someone is demonstrating that I'm not working in the right direction. But I really believe that in what I've been discussing with you, there is a lot of material that could be used for future research and work in the next years. I think we have maybe 10 minutes if there is any question or any comment or whatever you want to do. If there is nothing, we will complete. I don't know if the people connected can also intervene or not. No. Sure. Yeah. So also those who are connected at a distance can unmute the microphone and ask whatever they want, with permission of Gerald, which is the host here. Everybody has permission. Matt, please. Just if you want to be listened, come closer. I mean, to the people connected, they are listening through this microphone, and you can stay on that side. That's good enough.
Yeah. So my question was: is interesting work in New Zealand at the moment, looking at some low damage seismic design guidelines, and they're looking at introducing just a very simple limitation of drift to 0.5%. So I was interested to see what your thoughts are on the introduction of something so simple. Would it be effective, or is the world of loss assessment so complex that you could actually be taking things in the wrong direction.
No, I think that a general measure of limiting the interstory drift is certainly a good measure. Certainly. I am convinced that most of the damage and consequently the loss in a building, not in all kinds of structures, in a building is more connected to the interstory drift than to anything else. But if you ask me how much you are diminishing the losses, this is a different question. This is the same kind of, say, conceptual step that we discussed for years, going from forces to displacement. Are you willing to design to have a response which is anyway better than, or are you wishing to design for something which is there? From another point of view, what I'm telling you is that if you limit the interstory drift to a low level, you are certainly obtaining good results, but you may be wasting resources. It might be that you could obtain the same result investing less resources. That's my point of view. So, Ger, Guido, any comment? Younger new students?
Can I ask a question from Zoom? First of all, thanks for the very interesting presentation. I just want to ask you something simple about
Please, first of all, tell us who you are.
I'm Karim, the PhD student of Carmine.
Good.
And I just would like to ask you about the selection of the intermediate point that helps defining the shape of the loss curve. So you said that it could be anything, but I think at some point it should be a bit meaningful to the purpose of the structure that you are designing, for example. So could you please give me some guidance about that?
This is a very well picked up point. You know, I have not a clue. I was just guessing, and you know that guesses are often very dangerous. You may remember that the reason why we are designing for something which has a 10% probability in 50 years was just because Jenkins and came out with an example, and they took that example, and then the example became the rule. I have no idea. I think that I was just guessing something, probably 20-30% and so on, but I think that this kind of the answer can come only from serious analysis, sensitivity analysis of different cases, and it may well end up with different responses or answers for different kind of structures. It's very likely that in my opinion, that the best point is not the same, for example, in building and bridges. The kind of damage and loss is very different. In bridges, you have only a few non-structure elements. The typical case is a joint. You know that in a large bridge, the cost of a joint could be very, very high, could be millions of euros. And you know what the problem is that you think, okay, if I have a damage there, I substitute the joint, right? But sometimes to have a second joint, you may have to wait for 4 months or 6 months before it is produced and delivered on place and so on and so forth. So I'm saying that the answer is not simple, because the answer depends on the response of the structure. But after all, it took a long time to us to try to to calibrate force reduction factor, to calibrate ductility, to calibrate even equivalent damping in displacement-based design. It may take some time to do this kind of reasoning.
Yeah, okay. I have another question, if you allow me, please. So I really like the idea that if you want to apply also loss-based design, let's account for the indirect losses resulting from the downtime, which is very interesting. I got a bit scared when I saw that this kind of loss could be 3 or 4 times greater than the direct loss, but okay, at the same time, it's on the side of the earthquakes that are very rare. So maybe in terms of expected annual loss, it will not increase it that much. But let's say that you have a significant effect of the downtime in any geographic location. How you think this would affect the real design of the building in terms of sizes of structural elements? Because what I recall, for example, in the ASCII, they design for like 2% risk targeted maps. I don't remember if I'm saying the term well, but in any case, I think they are considering direct losses only. So I'm just trying to imagine how would a real structure be in terms of sizes, dimensions, reinforcement, when you also add the indirect losses that are going to be very significant in some cases.
Look, indirect losses for normal buildings, I mean residential buildings, are likely to be very much in the same range, and in my opinion, not in the range of 3 or 4 times, probably in the range of same as could be between 50 and under 50% of direct losses. But when you go to, in the case of buildings, when you go to large indirect expected losses, probably for those kind of buildings, you will have to design anyway for, say, low interstory drift and so on, because you need a continuity of use of those buildings, like the case of hospital, like the case of, I don't know, center of civil protection, or, there are a number of buildings. The case is different when you deal with bridges, because in that case, it could be really many times. If you lose the functionality of a major bridge, that could be. I did some calculation of what the societal cost of not using the bridge in Genova after the collapse on you remember now 3 years ago, and my calculations were that the losses were in the range of 2 million per day. So it means that every 3 months that the bridge remained closed, you were more or less paying the reconstruction. This is somehow searching for new vision for this sort of cases, but that was a very major bridge. But imagine that you have this kind of situation for a small bridge, a bridge that could cost 2 million. But if you stop that bridge, consider also another point, in bridges and roads, the capacity of a bridge is finite. Cannot increase. You cannot take the traffic on one bridge and move it to another one, because the capacity is like the capacity of a pipeline where you have water flowing through. If you know that the distance between cars is a certain level, at the velocity it cannot be higher than a certain level, then you can calculate what is the maximum number of vehicles that can pass in 1 hour. If a bridge is close to that value, you cannot add traffic. If you add traffic, you end up with a traffic jam. And if this is permanent, the traffic jam is permanent. So then there is another case, which is the case of industrial buildings. That's another kind of extreme case. In the past, very stupid choices have been made, because there have been cases of industrial buildings where they spend, I don't know, 2, 3, 4, 5 million for the building, and they put inside the building something whose value was 50 or 100 million. Why to save on the building? Why? I mean, spend more on the building and make it working properly in case of an earthquake. So again, I do not have a specific answer to your questions. My answer is there is a lot of work to be done.
Thanks a lot.
I have a question. Roberto Gentile from UCL.
Yeah, please.
Thank you very much for the presentation. I loved it. And I believe that your guess about the indirect losses is very useful, let's say, for us, that we cannot really make an educated guess and publish it. So once you've published it, we can use it. But now the question is how we test it. How do we test it? How do we calibrate it? And I'm not talking about calibrating indirect losses. I'm talking about calibrating the ratio. Thank you.
I don't know. That's my answer. Anyway, no, I think that it is actually possible. You know, my guess, as you were saying, are possibly educated guesses. Thank you for your kindness, but we may discuss, and actually this data could be discussed in a number of places. Could be discussed with insurance and reinsurance companies, looking at what they've been spending after an earthquake. Could be discussed with the civil protection, which has been repaying losses after earthquakes. So I think that there are actually experimental data that could be available. Maybe they have not been that easily available in the past, but if we put this as an effort, I think we can find it out. And as usual, you know, on one side you have numerical models, on the other side you have experimental data, and we always have to deal with the experimental data. In this case, experimental data are the consequences of events, and we have to go and grab and find out what the consequences have been. I think we do.
Okay, thank you.
Probably there is a class at 6 o'clock.
Okay, so thank you again to Michele for his presentation, and thank you for everybody who's joining online and everybody who came this evening. Sorry if I'm rushing and there's no more time for questions, but there's a class here in a few moments, so we had to maybe accelerate some things. I think that's it. So everything we've been talking about and has been said here will be recorded and made available online, so you can catch up or have a look again if you want, and all of the information, I'm sure Michele would be happy to pass of all the examples and the material presented. You know, it's available in different places around the world. So yeah, there's a lot to be done and a lot of new ideas to take forward. So I think we'll leave it at that. So just last thing, thank you to Michele, I guess.
Okay.